not quite sure how much calculus you've had and where we should really begin.
Yeah, here, I can take some pictures and email them to you really quick.
Okay. Did you get the slope of the tangent line?
Yeah.
Go over that. That's so important in calculus that that's almost the starting spot.
All right.
I mean, limits are the starting spot because the difference between algebra, geometry, trig, and calculus is limits. That's really the first time you encounter limits is when you get into calculus, and you don't really see them in any other kind of math. So limits is what differentiates, bad word to use, limits is what separates all the math prior to calculus from calculus.
Yeah.
And kind of all about dividing by very small, you can't divide by zero, but you can divide by very small quantities that approach zero. And you can solve a lot of problems that aren't solvable with non-calculus.
Yeah.
You want to get some of the problems? Or shall we talk about the slope of the tangent curve?
We can talk about that. Well,
let's talk about the slope of the tangent curve. Let's just review that, and then we can maybe look at some of your problems. All right. If I take the function y equals x squared, parabola, and naturally I didn't draw it correct because I want it to be, I have nothing but curves like that. Now, pre-calculus, I could calculate the average rate of change of this function between any 2 points. In other words, if I want to know how that function changes between 1 and 2, then it's the slope of that line, right? It's the slope of that secant line.
mm-hmm.
Because the average rate of change is rise over run.
Mm-hmm.
So whatever this would be, that would be what? Let's start calling that point f of 2. And let's call this point f of 1. Now, f of 2 is clearly 4. F of 1 is 1, right? So if I want the average rate of change that this function is doing between 1 and 2, I would take f of 2 minus f of 1, that's the rise, and divide it by 2 minus 1, that's the run.
Yeah, I just sent you the worksheet.
Ah, okay. Did you send it to my email or my phone?
Your email.
Okay, because at the same time I got some text messages.
And I figured we could start working on my worksheet next week, but
yeah, okay, hold on one second. It was funny. These text messages came in exactly at the same time. Just one moment. White with black front on the oven. They're replacing my stove, and I had to tell them what color it was. Sorry about that. Okay, let me, let's finish talking about this. This is so important in calculus that let's finish going over this. So I know how to take the average rate of change of this function.
yeah.
Taking the instantaneous rate of change at this point right here becomes a little bit more problematic, because if I
At 1?
Yeah, if I want the slope of the tangent line when x is 1, how do I do that? In other words, the rise is 0 at that point, and the run is 0. So I basically would end up with 0 over 0, not an easy thing to figure out the slope of that tangent line.
Yeah, we went over this. I can't remember what the rule is called, but
Well,
you take that.
It's the limit definition of first derivative. What
Yeah.
first derivative is all about is instantaneous rate of change, not average rate of change.
Yeah.
If you want to know the rate of change of this function at 1, we need to figure out the slope of that tangent line. Well, the slope of that tangent line,
It's 2.
yeah, but we get it by, let's go through the logic.
I think it was f of x or f of x plus h.
Now you're talking. All right.
Something like that, yeah.
If we make some arbitrary x on the x-axis, okay, that's not at 1 anymore, it's just called x, and I go some distance to the right of it, h, well then this point here must be x plus h, right?
Yeah.
Okay. Now, if I want the slope between x and x plus h, the formula is going to be f of x plus h, this point here, minus f of x, that's going to be the rise,
Over.
and the run is going to be x plus h minus x.
Yeah. That's what I was trying to remember.
Yeah, so we end up with just h in the bottom. And what we want to do is the slope of the tangent line is going to be the slope as the secant line approaches the tangent line. Right now, that secant line is not a tangent line, but as h gets smaller, in other words, as this point x plus h goes to x, as h goes to 0, this secant line approaches the tangent line. And we end up with the slope of the tangent line by taking the limit of this function as h goes to 0.
Yeah.
And that is the definition of first derivative. And first derivative means exactly that. It's the instantaneous rate of change, or you could call it the slope of the tangent line. But that's what derivative is all about, is it's the rate of change. And you can have a second derivative, in other words, what's the rate of change of your rate of change? You can have a third derivative. What's the rate of change of the rate of change of your rate of change? So there's no limit to how many derivatives you can take of a function. But if we apply it to this definition, well, what is if this y, I should have written it as f of x, it's better, it's more robust, means the same thing as y, it's just better notation because it allows me to substitute variables or numbers in. So what is f of x plus h? If we're going to apply this formula, we need to know what f of x plus h is.
Mm-hmm.
What is it? If f of x is x squared, what is f of x plus h?
X plus h squared.
And in the that's that part. And then I'm going to subtract off f of x, which is just x squared.
Yeah.
Divide the whole thing by h and take the limit of it as h goes to 0. Well, what happens in all of these is, let's expand that. So what's x plus h squared? It's x squared plus 2xh plus h squared. So that's that part.
Yeah.
And then I'm subtracting x squared and dividing by h. Well, what's going to happen here is no matter how complicated the function is, we chose an easy one, x squared. But even if we would have chose a hard, complicated function, every term that does not have an h is going to disappear. Notice that x squared goes away, and I'm left with just this in my numerator, which I can now factor out an h, and I'm left with 2x plus h in the numerator. The denominator still has that h, which is now going to cancel, and I'm left with finding the limit of 2x plus h as h goes to 0. Well, what is that limit? What's the limit of 2x plus h as h goes to 0?
2x.
And that is the derivative of x squared.
Yeah, but what's the shorter way? It's
the power.
Isn't it? Yeah, the power rule. That's multiplying the.
Yeah. The power rule says that if y is equal to x to some exponent, then y prime, which means also dy dx, equals n times x to the n minus 1. So that's the power rule. In other words, for x squared, it would be 2 times x to the 1 power, which is 2x. Once you learn the 4 rules, you don't ever use the other definition. Okay? It's a lot like all math subjects. For some reason, they insist upon starting out math subjects with almost the most difficult part.
Yeah. Which
in this case, the limit definition rule is so much harder to do than the 4 rules that you can use: the power rule, the product rule, the quotient rule, and the chain rule. Did you get all 4 of those last year?
No, I think we only covered the power rule.
Just the power rule? Okay.
Yeah, I think that's the only one we definitely went in depth with.
Yeah, well, the power rule works for polynomials where, because the derivative of the sum is the same as the sum of the derivatives, if I give you a polynomial like this, you can take the derivative using the power rule because there's no multiplication of variables going on or functions.
Yeah.
It's all addition and subtraction. So if I apply the power rule to that, I get this, and the derivative of all constants is 0.
Yeah.
No matter the constant. So the power rule works great on polynomials.
Yeah.
Doesn't work as well when you're multiplying stuff together. If I am multiplying x times, say, the square root of x minus 1, I can't apply the power rule directly to that. I've got to use the product rule because I'm multiplying that function times that function. Mm-hmm. Or if I had x sine x, that's multiplication. So anytime you have 2 different functions being multiplied where you can't actually distribute it, in other words, I can't distribute that. That's the most simplified way I can show that, and this. Then you have to use the product rule. And the product rule is actually pretty simple. It's if you have y equals a times b, let's use the letters they like to use, which are u and v. If u and v are functions of x, and I want to take the first derivative, then it's u times the derivative of v plus the reverse, plus v times the derivative of u.
Okay.
Okay? So if I had, say, y equals x sine x, then y prime would be what?
It would be
You get the derivatives of the trig function, John? Have you had that?
a little bit. I think I forgot most of them.
Let's go over them. In fact, let's start going over those immediately, because that's something you're definitely going to want to memorize. Okay?
Yeah.
You don't want to have to look these up. What's the derivative of that? Cosine. In other words, if this is y prime.
Okay.
The derivative of cosine is minus sine.
Okay.
The derivative of tangent is secant squared. The derivative of the other three are a little tougher to memorize. Let's start with cotangent, because once you know the derivative of tangent, the derivative of cotangent, notice that the derivative of each cofunction is negative, and it's cosecant squared.
Okay.
Notice that cotangent is the cofunction of tangent, and cosecant is the cofunction of secant. Just like sine is the cofunction of cosine. So this pattern stays. In other words, when I want the derivative of secant, that's equal to secant tangent, which means the derivative of the last one, if you're trying to memorize these, would be what's the derivative of cosecant? Well, you know it's going to have a negative sign in front of it, and it's the cofunction of each of these. So it would be cosecant x cotangent x. In other words, if you memorize the derivatives of these three, the derivatives of the cofunctions are always negative the cofunction of this. You see what I'm saying? You see the pattern? In other words, if you know the derivative of tangent x is secant squared, then you know the derivative of cotangent has to be negative, and whatever the cofunction of secant squared is, that's cosecant squared.
Yeah.
So you really only have to memorize three of these. If you memorize the three that I have listed as 1, 2, and 3, you can always figure out the others. But you end up memorizing this one whether you try or not. And the two that people have the most trouble with are probably the secant and then these bottom three here are tough to kind of memorize. But it's worth memorizing them, and I mean memorizing them. You don't want to have to look some of this stuff up all the time. Even though your calculus book may have an opening page that gives you all these derivatives, the key derivatives and integrals, you want to have those in memory, only because it comes up so often that you have to take the derivatives of these trig functions.
Yeah.
Okay. All right, so let's go back and do this product rule. I'm not going to spend a lot of time teaching you new stuff yet. I think it's more important that we kind of review the stuff you've already had. But the product rule is easy enough that we'll go over it just so you'll know what I'm talking about. So if y prime is equal to the first function times the derivative of the second plus the second function times the derivative of the first, what would it be here? What's the What's the first part going to be?
It would be 1.
You know what? I'm going to suggest always following the same pattern.
Okay.
In other words, we have a plus sign there, which means I
Yeah.
could reverse these and everything would be fine.
Yeah.
The problem is that when you do it either way, it makes it actually a little harder to do and remember.
Mm-hmm.
So I always do it the same way. I always do, my first step is always going to be x times the derivative of the second function.
Yeah.
Well, what's the derivative of sine?
Cosine x.
Plus the reverse of that. And
So cosine x times x.
no, the reverse of that is the derivative of that times that.
Oh,
Derivative
yeah.
of x, which is 1 times sine x.
Oh, okay. So
That's the derivative of the product of x times sine x.
yeah.
Okay. Did you have the chain rule at all?
No.
All right. That's the next place it gets a little tricky. You have the power rule.
Yeah.
You have the product rule.
Okay.
The next most complicated one is the quotient rule, where if you have y equals some function divided by a function, another function, this one gets relatively complicated. Y prime becomes the bottom times the derivative of the top, and this time it's minus the reverse, which is the bottom's derivative times the top, all divided by the bottom squared. So when you have two functions that are being divided, it's much harder to figure out the derivative. This gets pretty complicated pretty fast. And if you're taking second derivative, it really gets complicated quickly.
Mm-hmm.
So you have a product rule, you have a quotient rule, and then the last rule you have really is the chain rule. And I won't go over the chain rule. It's a little bit more difficult to explain. I won't go over it yet. But between those four rules, the product rule, the power rule, the quotient rule, and the chain rule, I can differentiate all functions, no matter how complicated.
Yeah.
Pretty straightforward. And it's
Yeah.
not that hard. It's pretty much plug in and solve. It's not as hard as using the limit definition. But that limit definition is very important to understand. And the hardest thing for people to understand is labeling this point. The y value on that point is f of x plus h. And we're constantly referring to the y values on things. Let's take something else that it sounds like you had. And that's just a little bit of integral calculus. If I take that function, which is y equals x squared plus 2, and I want to find the area under the curve between 1 and 2. Well, precalculus doesn't do areas of curves very well.
Yeah.
Geometry is all about areas of straight-lined figures, squares, rectangles, triangles, circles also, but that's about it, is circles are about the only curved figure you work with where you have to figure out areas.
Yeah.
So in calculus, you need to be able to know the area under a curve. Well, the area under that curve isn't terribly easy to figure out. We don't have any geometry to do it, so what we do is we split it into a bunch of rectangles that approximate it.
Mm-hmm.
Well, the concept of this F notation is that the area, in other words, I'm going to calculate the area under that curve by summing up all of these rectangles, the areas of each rectangle. Well, how do I get the area of rectangle number 1? It's height times the base. So it's whatever the thickness is of that rectangle, and I can make it whatever I want. In other words, I could put 10 rectangles under that curve, or I could put 100, or I could put 1,000,000. But the more rectangles I put in between these 2 points, the more accurate is my answer. If I only draw 2 rectangles, I get a very rough approximation of the area under that curve. But if I draw 10, I'm much closer to the true area. And if I draw 100, I'm closer still. Well, the secret is to let the width go to 0. Just like letting h go to 0 when we're looking for the slope of the tangent line, when we're looking for area under curves, we're going to let this width here, delta x, go to 0. And then the height of the function is always going to be some f of, in this case, it might be 1 plus 1/10 if I had 10 rectangles in there. Then this point right here, to define the height of the first rectangle, is defined as not plugging in 1 and 1/10 for x, but it's defined as being f of 1 plus 1/10. In other words, this point right there is 1.1. So if I want to find the height of that rectangle, I'm going to figure out what f of 1.1 is. And so f of 1.1 is 1.1 squared plus 2. So that's the height of that first rectangle. And the width, in our case here, is 1/10. Because we've taken this distance between 1 and 2 and divided it into 10 rectangles. Each one of them being 1/10 in width. What area under the curve is integral calculus.
Yeah.
If you had to use 3 words only to describe differential calculus, it would be instantaneous rate of change, or slope of the tangent line. But slope of the tangent line, what it really means is instantaneous rate of change. When you're driving your car and you're on the highway and you look down at your speedometer, it's giving you your instantaneous rate of change. That's what velocity is.
Yeah.
Whereas if you drove to Colorado Springs in an hour, you could say, well, you averaged 60 miles an hour going down there. So your average rate of change would be 60 miles an hour. But at any point in time on that trip, you might be going 40, you might be going 30, you might be going 70 sometimes. So your velocity is actually a first derivative of a position function. And acceleration is the second derivative. Notice what your acceleration is. When you step on the gas pedal, you're changing your velocity. Or if you step on the brake, you're changing your velocity. So the acceleration is a measurement of the change in your velocity. And the velocity is a measurement of the change in the position of the particle, whether it's your car or a particle moving along the x-axis or moving along a curve. All right. I know we got started a little bit late. I'm not sure. I think it was like 11:20. I don't know what your schedule is. I'm happy to go till 11:20 if you want. I mean, we got started at like 10:20, I think.
I have stuff I need to get ready for.
Okay, I thought that might be a consideration, so I didn't want to automatically just go to 11:20. Okay, so we are set for next Tuesday and Thursday at 10 a.m. for half-hour sessions.
Yeah.
And if you could, we'll go over your summary review material when we do those.
Yeah.
And you've emailed me all of those, or?
Yeah, I emailed you. It was just 2 pages, 18 questions.
Okay, good. So we've got 18 questions to go over. Well, that'll be good. With half-hour sessions, we'll probably be lucky to cover all 18 of them. I don't know. Okay. Well, Lucas, have a good weekend, and I will talk to you. On Tuesday, I will just text the meeting ID number to your phone number, just like I used to.
Yeah,
Okay.
that'll work.
Sounds good.
Okay.
Bye-bye.
Bye.